Hey everyone, welcome. So today, we're going to crack the code on a part of math that sounds pretty intimidating but is actually, well, it's incredibly elegant. We're talking about complex numbers. Think of it like this. They're a key that unlocks this whole other dimension of math. Let's dive right in. All right, I want to start with a question for you. Just think about it for a second. What number, when you multiply it by itself, gives you -1? I mean, if you square a positive number, you get a positive. And if you square a negative number, you also get a positive. So where does that leave us? What is the answer? You know, that simple little question, it actually shows us a wall. It's like a barrier that the numbers we use every single day, what we call the real numbers, just can't break through. Okay, so here's what that problem looks like in algebra. X squared plus 1 equals 0. Now to solve for x, you'd have to find a number whose square is -1. And using the numbers we all know and love, it's impossible. We're totally stuck. But, this is what I love about math. When we hit a wall like this, we don't just throw our hands up and quit. Nope. We invent a brand new key to unlock a whole new world. And look, I know that sounds a little weird, inventing a number, but it's not as strange as you might think. We've actually done this before. Just think about negative numbers. We literally invented them to handle ideas like debt. They didn't really exist in our toolkit before that. Basically, when we need a new tool for our mathematical toolkit, we just invent it. So let me introduce you to our new key. It's called the imaginary unit, and we just use the letter I for short. Its definition is just beautiful and simple. I is the square root of -1. That's it. It's the answer to our impossible question. And this one little definition, it leads us to the single most important consequence, the one new rule you need for this whole topic. If I is the square root of -1, then it just follows that I squared has to be -1. This one fact is the key to absolutely everything else. And honestly, this is the best part. Seriously, if you remember one thing from all of this, make it this. I squared equals -1. That is the only new rule. Everything else, it's just the same old algebra you already know how to do, just one tiny addition to the rules of the game. All right, so let's see how this one new rule lets us do all the normal math we're used to, just with a cool new twist. Okay, so any number that uses this new I tool is what we call a complex number. They all follow the standard format, A plus BI. A is the real part, just a regular old number, and B is the imaginary part. It's the one that gets multiplied by I. And you're going to see this is super intuitive. When you're adding or subtracting these things, you just combine the stuff that looks alike. You add the real parts with the real parts, and the imaginary parts with the imaginary parts. It's exactly like the algebra you've always done. All right, so addition is easy. What about multiplication? Well, it's just as straightforward, believe it or not. Let's try multiplying these two complex numbers together. So we just multiply them out, like we always would, using FOIL. You remember? First, outside, inside last. Then we combine the I terms. And then, bam, here's where our one new rule comes into play. Anytime you see an I squared, you just swap it out for a -1. From there, you're just cleaning things up to get the final answer. See? It all flows from that one simple rule. Okay, now for the one that usually trips people up, division. But don't even worry, because we've got a secret weapon that makes it surprisingly simple. And that secret weapon? It's called the conjugate. All it is you take the complex number and you just flip the sign in the middle. So the conjugate of A plus BI is A minus BI. This is the little magic trick that makes division work. So how does this magic trick work? Simple. You take the denominator, find its conjugate, and then you multiply both the top and the bottom of the fraction by that conjugate. And the reason this is so cool is that when you multiply the bottom by its conjugate, the I terms in the middle, they always cancel out. Poof, gone. And that leaves you with a nice, clean, real number on the bottom. After that, you just tidy up the top, split it into its real and imaginary parts, and you're done. Problem solved. Okay, before we go any further, let's just quickly cover a few common mistakes people make. Number one, by far, is just forgetting that I squared equals -1. It's the key to everything. Next, sometimes people get their real and imaginary parts mixed up when they're adding. And last, for division, you've got to use the conjugate. It's not optional, it's the whole trick. So up to now, this has all been, symbols on a page. It's been algebra. But what if we could actually see these numbers? Let's try to give these numbers a place to live. So you already know the good old coordinate plane, right? With an x-axis and a y-axis. Well, the complex plane is pretty much the exact same thing. We just give the axes new names. The x-axis becomes the real axis, and the y-axis becomes the imaginary axis. And suddenly, this whole idea just clicks into place. That number, 3 plus 4i, it's not just some abstract thing anymore. It's a place. It's a point on a map. You just go 3 units over on the real axes and 4 units up on the imaginary axes. Boom! That's it. It's just the point 3, 4. Okay, so we can define them, we can do math with them, we can even draw a picture of them. But so what? Why should you care? Let's connect this abstract idea to where it gets its real-world power. The funny thing is, these so-called imaginary numbers are absolutely essential for describing the real world. I mean, they're everywhere. They're used in electrical engineering to figure out AC circuits, in signal processing, that's your phone, your Wi-Fi, in physics to describe waves, even in computer graphics to rotate stuff on your screen. They're basically a cornerstone of modern science and tech. And that kind of brings us to our final thought. We started this whole journey with a problem that seemed completely impossible to solve with the numbers we had. And the answer wasn't to look harder for a solution that was already there. The answer was to invent a new tool. It really makes you wonder, right? If inventing one new type of number can solve this impossible problem, what other impossible problems are out there right now just waiting for someone to invent the right kind of math to crack them wide open? All right, I want you to forget everything you probably learned in high school geometry. Seriously. Today, we're going to unlock a completely new way of seeing the world, a kind of secret language that describes how every single shape moves, turns, and flips. This is the secret language of movement, and you're about to become fluent. So take a look at these two shapes. I mean, your gut tells you they're the same, right? They look identical, just one's kind of flipped and moved over there. But in the world of math or design or engineering, it looks the same, just doesn't cut it. How do you actually prove it step by step with 100% certainty? Well, the answer isn't about getting out a ruler and measuring every little side. It's about a totally different way of thinking. It's about understanding the actions that connect one shape to the other. And that is the secret language of movement. So here's our game plan. We're going to start with this core idea, learn the 4 basic words of this new language, and then we'll use them to unlock some of geometry's biggest secrets. We're talking congruence, similarity, even symmetry. Trust me, by the end of this, you'll have a new geometric superpower. Okay, so let's jump right into that big idea. We are fundamentally shifting our perspective here. We're going to stop seeing shapes as just static objects sitting on a page and start seeing them as things that can move and change, but only according to a very specific set of rules. And this action, this movement, has an official name. It's called a transformation. The best way to think of it is just as a rule or a set of instructions. It's a rule that tells every single point on a shape exactly where it needs to go. The original shape moves, and the new shape that appears is called its image. This is our official recipe for movement. Now, the cool thing is, this whole language of movement really only has 4 basic words, 4 fundamental actions, and you already know what they are. You just know them by different names. We can slide something, we can turn it, we can flip it, or we can resize it. So let's just make it official. First up, let's talk about translation. This is the simplest one. It's literally just the slide. Imagine picking up your coffee mug and just sliding it across your desk. No twisting, no turning it upside down. Every single point on that mug moves the exact same distance in the exact same direction. Now, the formal math rule is pretty simple. You just add some numbers to the coordinates. But look at that properties row. That is the key insight right there. A translation changes a shape's location, for sure, but absolutely nothing else about it. The size, the angles, even which way it's facing, all stay exactly the same. Okay, next up is rotation, which is, you guessed it, our turn. To pull this off, you need 2 pieces of information. You need a fixed point to pivot around, we call that the center of rotation, and you need an angle that tells you exactly how far to turn it. The rule for a 90-degree turn might look a little weird, with the coordinates swapping and changing signs, but again, The important part is the properties. Just like a slide, a turn leaves the shape's size and all of its internal angles completely untouched. Our third move is reflection, or the flip, and it's exactly what it sounds like. You're creating a perfect mirror image of the shape right across a specific line. We call that the line of reflection. The rule for flipping over the x-axis is dead simple. You just flip the sign of the y-coordinate. But wait, here's a huge twist. Look at those properties. While the size and angles are still preserved, the orientation is reversed. Left becomes right. This is the very first move we've seen that fundamentally changes which way the shape is facing. And that brings us to our last basic move, enlargement, or what's also called scaling. This is simply the resize. The best way to picture it is just pinching to zoom on your phone. You've got a center point and then a scale factor that tells the shape whether to get bigger or smaller. So the rule here is just simple multiplication. But this leads us to the most important difference of all. Unlike slides, turns, or flips, enlargement is the only move that actually changes the size of the shape. But notice what it doesn't change: the angles. The shape gets bigger or smaller, but it never gets warped. Okay, so that distinction, changing size versus keeping it the same, that is absolutely everything, because it lets us sort these four moves into two very powerful clubs. And this is where the really big ideas start to come together. So on the left, we've got what are officially called isometries. It's just a fancy name for any transformation that preserves distance. In other words, it keeps the size the same. This is our same size club, and it includes translations, rotations, and reflections. And then over in the other club, all by itself, is enlargement, the one move that changes the size. So why did we just go through all of that trouble sorting our moves? Because we've just arrived at the payoff. This simple grouping is the key to finally, and I mean truly, understanding two of the biggest and most important ideas in all of geometry. And here it is. This slide is the whole thing. Two shapes are congruent if you can slide, turn, or flip one to land perfectly on top of the other. You can only use moves from the same size club. And two shapes are similar if you can do all that, but you're also allowed to resize it. That's it. All those complicated rules you might have learned in school, they're replaced by this one beautiful, simple idea about movement. Okay, now that we have this incredibly powerful way of thinking, we can unlock other beautiful ideas too. So let's take a quick look at symmetry, because it's really just a special case of what we've already been talking about. So what actually is symmetry? Well, in our new language, it's when you can perform a transformation on a shape, like a flip or a turn, and the final image lands perfectly back on top of the original. The shape is basically unchanged by the move. A human face has reflectional symmetry, a starfish has rotational symmetry. And for rotational symmetry, we can even measure it. We talk about its order. To find it, you just fix the center of the shape, turn it one full 360-degree circle, and count how many times it looks identical to how it started. A square, for instance, will match its original outline 4 times on that journey, at 90 degrees, 180, 270, and finally back at 360. So we say it has a rotational symmetry of order 4. So why does all of this matter, beyond just giving things fancy names? Because thinking in terms of transformations isn't just a definition. It is a problem-solving superpower. It's the kind of thinking they use at the highest levels, like in math competitions. And right here is the superpower in action. The next time you see a really complex geometry problem, don't just stare at it and start measuring. Move it. Ask yourself, what happens if I rotate this piece? What if I reflect this part across a line? So often, the solution isn't in the shape itself, but in the hidden symmetry that you reveal when you start playing with it. So, let's end with one final challenge. Picture a point at coordinates 1, 2. If you rotate that point 90 degrees counterclockwise around the origin, where does it land? Just take a second. If you can actually see it in your mind, snapping into its new place at -2, 1, then you've done it. You're no longer just solving a math problem. You're thinking in the language of movement. You have officially unlocked geometry's superpower.